Last time we started to study first-class constraint systems. So we gave a physical interpretation of it. So we understood that the reduced space is a space of gauge orbits, which foliate the constraint surface. And we ended with discussing geometrical interpretation. So let me remind you these definitions, which we had already at the end of previous lectures. So distribution on a manifold sigma is a subbundle D of the tangent bundle was a manifold, which means, if you're not familiar with the bundle terminology, which means that at each point of sigma we have a subspace dp of tp sigma, so a subspace of the tangent space. And then we say that distribution D is invertible if there are two vector fields belonging to D, their commutator also belongs to D, right? And then another piece of terminology is that D is called integrable if, well, this is, for me, I only do local story. If locally, at least locally, for any point, there exists submanifold of sigma such that EXL is equal to dx for any x in L. So it's a submanifold such that so our distribution is like this. It means that there are some, in one-dimensional case, distribution is just a one-dimensional distribution. It's enough to say what is a vector generating the subspace at a point. And this is a picture for integral submanifold. So for instance, submanifold here, integral submanifold can be like this. Well, this picture is not very well, something like this perhaps, not very good picture. But what is clear that if there is an integral submanifold, then our distribution coincides with its tangent space at points of this submanifold. And then we quoted the well-known theorem, so-called Frobenius theorem, which says that for sigma finite dimensional, involutive equals integrable. Of course, it's clear that integrable implies involutive, but other way around, that the statement is less trivial statement, and it's a statement of Frobenius theorem. The idea of the proof is again very much in spirit of what we are doing. So if we pick a basis in our distribution, so we pick vector fields R alpha belonging to our D, such that they form a basis, so their linear span is D, right? So what does it mean? Linear span over functions, right? So at each point we have vectors R alpha. Well, maybe let me write it like this. So if we take a linear span of vector fields R alpha taken at point P, then this is dP. And of course, it's a good idea to remove P here, right? Just to say this, if it holds for all points. So then we say that we pick a basis in our distribution. It's very convenient because any vector, if R alpha form basis in D, then any I don't know, Y in D can be represented as Y alpha R alpha. Strictly speaking, there is no need to require R to be independent, so usually it's of course very convenient to work with linearly independent vector fields R. In case if they are linearly independent, this decomposition is unique, of course. Okay, so the idea of the proof, as I said, is to look for functions annihilated by the distribution. So these are precisely, in physics terms, these are precisely the observables we were discussing last time. And then use the result from partial differential equations, that because it's a system of first order partial differential equations, so it is clear that necessary, but in fact sufficient condition to have like maximal number of independent solutions is that R alpha, R beta, the consistency condition. So I go on X, I is again 0, so it's satisfied. And this is the case if R alpha, R beta is proportional to R again, so belongs to the distribution for some functions U. So it's not a Lie algebra in general. Usually it's even 0 in use in good cases. So but in general, these are functions on our space. So what we are doing, we are looking for functions annihilated by the distribution. So it's enough to require our functions to be annihilated by vector fields R alpha, and then we check consistency. So we apply R beta to this equation. We commute. It should be again 0, but this implies this. And this is automatically satisfied if the commutator of R is again proportional to R, which is precisely the condition of involutivity, right? So if our D is involutive, then R alpha, R beta is again proportional to R, right? Okay, so it means that we can find such functions xi, then we can complete our if pick maximal independent number of such functions as part of coordinate systems, then complete by another functions y alpha to a complete coordinate system, so that this is coordinate system on sigma, right? And in this coordinate system, because R annihilate y, R alpha takes the following form. It's R alpha beta of xy d over dy beta, right? It can't have derivative with respect to x because it must annihilate x, right? And then our integral submanifold is just xi equal to constant I, right? And functions y alpha become coordinates if we restrict them to a particular integral submanifold. They become coordinates there. Okay, so it's exactly the situation which we have in first-class constraint system. This is the reason why I used exactly the same conventions. So let's do this relation between, let's say, geometry and physics. So first-class constraint system, This is like geometry. So here we have our constraint surface. Surface sigma. Here we have our manifold sigma. And then we have distribution. We have this R alpha gauge generators. They arise for us as Hamiltonian vector fields generated by first-class constraints and restricted to the constraint surface. Recall that they are tangent. So here R alpha is just particular basis for D. Here linear span of R alpha is a distribution. Here it's a distribution D. Okay. What else? We have here gauge orbit. It's a collection of points. You remember the definition which we can get by evolution with trivial Hamiltonian but generic Lagrange multipliers. And here it's of course integral submanifold. What else? These functions observables. These are R alpha f equals 0. These are functions annihilated by the distribution, right? And finally, we have our reduced phase space, which is space of gauge orbits. Here it's of course space of integral submanifolds. It's also called like quotient space of our manifold by the integrable distribution. But of course, globally it can be quite ill-defined. That's a subtle thing. That's why it's important to work with this space in terms of observables, not in terms of the, because in sophisticated situations, usually the space is very non-linear, very non-local, and it's difficult to work with it. But the space of observables, the functions are annihilated by the gauge distribution, this distribution generated by gauge transformations, gauge generators are alpha. It can be still a reasonable. It can be still a reasonable space. So you see that precisely we have the concrete realization of this geometrical picture. This is a standard story in differential geometry, in distributions. So in our setup of first-class constraint systems, we precisely get this setup on the constraint surface. But what is additional with respect to geometry, what is special? The additional ingredient is symplectic structure. Well, strictly speaking, on sigma we have presymplectic structure, which means possibly degenerate presymplectic structure, which is just a pullback of our symplectic structure on M. So let me put M. So on our phase space, we have a symplectic structure, and then we just restrict it to our sigma. And E is an embedding of sigma into the phase space. And in general, in general setup in geometry, we don't have it. And let me remind you the exercise which I gave last time is to check that this symplectic, this presymplectic, this degenerate structure becomes non-degenerate if we path to the space of gauge orbits, to the reduced phase space. So indeed, if it is well defined, we really recover a symplectic manifold somewhere hidden deep inside our first class system. Okay, good. Let me also remind you that another way of thinking about observables and physical interpretation of first-class systems is to work in terms of the initial phase space, not to reduce to constraint surface, because again, constraints can be sophisticated nonlinear functions, and in field theory they can also be differential. They can be actually differential equations where derivatives only concern spatial directions. That's why it's also difficult to work even in terms of sigma in field theory. In mechanics, it's usually still okay, but in field theory, even sigma is a tricky thing. For instance, in sigma, in Maxwell, for instance, I'll give this as an exercise to be discussed on the seminar because we don't have much time on lectures, but this is a very basic example, Maxwell theory, and it has to be understood well. So we'll get back to it. So for instance, in Maxwell theory, so where we have our A mu field and Lagrangian is -1/4 dA squared, the standard Maxwell Lagrangian, I'm sure you all know it. Then if we pass to Hamiltonian description, of course, we need to separate time and 3 spatial dimensions. And then we can rewrite the Maxwell system as a constrained Hamiltonian system. Actually, let me do this as an exercise. Show that first class action. Well, of course, I mean first class action of first class constraint system, just not to say all this. So the following form, so S equal to D for X. Here we have pi I D0 AI minus half. But I can't guarantee you that all signs are correct. Yeah, this is your exercise to check also. Okay, show that this action is equivalent. So let me also write what it depends on. So we have fields S, so we have PI, AI, and A naught. So 4 components of Maxwell potential: the spatial components, the temporal component A naught, and momenta conjugate to AI. It's very easy to check that actually pi I is an auxiliary field. It can be eliminated from this action, giving the action determined by such Lagrangian. So what I'm saying is that it is equivalent to Maxwell. And if you look at it carefully, equivalent to this. Yes, so let me also explain conventions. So mu is split into 0 and I, the temporal and spatial index, and of course f mu nu is d mu a nu minus d mu a mu. Standard conventions. So this is nothing but the Hamiltonian formulation of Maxwell theory: free electromagnetic field, no sources, but so it's easy to find, to add sources. And it's easy to obtain. Well, of course, it's a simple exercise just to eliminate pi and to make sure that by eliminating pi, you get the usual Maxwell action. But also it's easy to get this action. If you, my advice is don't try to go to Dirac-Bergman procedure. It's quite a long story. In such a simple cases, it's much easier just to do partial Legendre transform. So if you look at Maxwell action, you see that you can do Legendre transform for all velocities, which means these guys associated to spatial components of the potential, but the temporal component of the potential, clearly A naught dot does not enter the action because it F naught naught is 0. So actually this A0 enters like this, and it should be interpreted as a Lagrange multiplier. So there is nothing to do. You just do a partial Legendre transform, you get an equivalent action, and then you check that this is a first-class system. So this is a first-class constraint, and this is Hamiltonian, and all conditions are satisfied. Because constraints depend only on momenta, so they commute with one another. Well, actually, you see, what does it mean? So this di, pi, these are first-class constraints. Why I'm saying in plural? Because these guys are parameterized by a spatial point of space, not of space-time, but only of space, because we're in Hamiltonian formalism, right? Our time is an evolution parameter. It is treated differently. So it's an infinite family of first-class constraints, but all of them depend only on momenta. That's why momenta commute with one another. That's why these are first-class constraints. Okay, good. And A naught, again, of X are Lagrange multipliers. And this is a very general feature that in relativistic field theory, temporal components of gauge fields are deep inside their Lagrange multipliers. But this is not so easy to understand without a bigger picture. So here we just check that this is indeed the case. Lagrange multipliers. Okay, good. So the exercise is to check that this first class action reproduce Maxwell, and other way around, that it can be arrived at just by doing partial Legendre transform. No need to do constraint analysis, in fact. As in most of real cases, you don't really need to go for sophisticated Dirac-Bergman procedure, which is a procedure to identify full set of constraints. But sometimes it is nevertheless needed. But I refrain from spending time on this procedure because, first of all, it's rarely really needed. And second, we just don't have enough of time for this. In realistic standard applications, you can easily find constraints and check that they give a complete set. Okay, good. So this is an exercise, and why I started to talk about this Maxwell system, because you see these are our constraints, and they are differential equations. Which means that if you want to work with sigma, this sigma is going to be an infinite dimensional surface embedded into an infinite dimensional space, and the condition which it defines is a differential equation. So, for instance, by doing local field redefinitions, you can't find good coordinates on this surface. You really need to do something, Fourier transform or something else, to work with this system. Fortunately, of course, with Maxwell, you can do everything because it's a linear system. But if it were non-linear, it would give extra problems. That's why it is clearly motivated that we need to be able to work with our constraint system without actually going explicitly to the surface sigma. Not to mention taking a space of gauge orbits. And this is at first approximation. This is a Dirac definition, let's say Dirac definition of observables, which we discussed already. This is a way to define observables and physical interpretation and evolution of such a system without the need to explicitly parameterize the constrained surface. So what are Dirac observables? Let me recall you that these are functions on our entire phase space, subject to the condition that f with constraints is 0 on the surface, and also that f is equivalent to f plus t alpha something. So two functions are considered, two observables are considered equivalent if they differ by a term vanishing on the constrained surface. So it's we checked it last time, if I remember correctly, that indeed Dirac observables, like inequivalent observables, which means space of classes of equivalence classes of such functions, inequivalent observables form a Poisson algebra. Poisson algebra means that you can multiply them and take a Poisson bracket, Poisson algebra. And if we really have a good reduced phase space, this Poisson algebra is precisely the Poisson algebra of functions on the reduced space. But the main message is that often this reduced phase space is not a good manifold and it's quite a sick object, but still this algebra is well defined and it makes sense. So it's preferable to work in terms of these functions. Though to understand what actually happens, what are gauge transformations, etc., it was a good pedagogical trick to really study the geometry of the constrained surface, of gauge transformations, etc., to understand what's going on. But of course, in reality, we prefer often not to do it and to work with Dirac observables or even a more sophisticated machinery, which is precisely this Hamiltonian version of Batalin-Vilkovisky formalism, which is known also as Batalin-Vilkovisky formalism, or it's also closely related to what is known under the name of BRST, BRST quantization. But we will get there. Okay, good. So our next and very important point before we get to this to this more general formalism is the gauge invariance of the action. Let me recall you that for us the starting point is the Hamiltonian action. And in fact, this action teaches us everything about constraint system. We kind of infer the physical interpretation and everything from this action. So the question I'm going to ask now is what is the role? How can we see gauge invariance, which we observed in terms of equations of motion and in terms of geometry of this constrained surface, etc., how it is reflected at the level of this Hamiltonian action. So let me remind you what it looks like. Okay, from which we get generalized Hamiltonian equation, interpretation, observed gauge symmetry, which takes solutions to solutions, and all that. So it turns out that this action is invariant. So this is precisely gauge transformations for this action. It is invariant under the following transformation. So delta ZA equal to ZA is T alpha lambda alpha, and delta lambda alpha is equal to epsilon. Oh, sorry. Epsilon alpha T. Plus some extra terms, and this will be an exercise to write them down explicitly. So these functions epsilon alpha are general functions of time, no constraints on them, and they are called gauge parameters. Gauge parameters. So the statement is that if we perform such a transformation, so if we change z like this, is infinitesimal transformation, so epsilon is an infinitesimal parameter. So we have the following transformation for z, and we have the following transformation for lambda, but I keep some extra terms here implicit, because it will be an exercise to find them explicitly. And let's check that this action S is invariant under such a transformation. And I'll show this in the simplified setup where these dots are going to be vanishing. And this is the setup simplified setup, when T alpha H is strictly 0 and T alpha T beta is also strictly 0. Then it's kind of simple. So let's consider the variation of this action under the gauge transformation. This is kind of simple. We know equations of motion, right? So variation of the action is just what? So we can write delta S, we can write as the integral dt of delta ZA equations of motion of Z plus delta lambda alpha equations of motion of obtained with respect to lambda. Just to simplify computations, because we know equations of motion, not to rederive them again, right? So what do we have? We have ZA, so I'm writing this, ZA with T alpha, epsilon alpha, and here I have my equations of motion. If you look back to our notes, note that the first equation, which is obtained by varying with respect to Z, looks like this. It is omega AB, no, yeah, omega AB Z dot B. I will see with signs. I might miss a sign. Omega AB Z dot B plus dBH plus dB T beta lambda beta. What it amounts to, you see our, oh, sorry, A here. Our index down is A. So this is just the Euler-Lagrange equations. Before we wrote them with index A down, then it is written in terms of Poisson bracket. But now it's convenient not to write the index, it's just to write equations as they are, because that's what we need here. Okay, so what do we see? We see that the second term, DAH multiplied by Z A T alpha gives just a Poisson bracket of T alpha and H, which is 0 by assumption. But your exercise will be to generalize this to the case when it is not 0, but as it should be for first-class system. If we look at this term, again, multiplied by this, we will find a Poisson bracket of T alpha T beta, which is again 0, so they do not contribute. So we only get first term, right? But first term is what? Let me rewrite it. It is ZA T alpha omega AB Z dot B. If you remember the definition of Poisson bracket, it's going to be ZA with T alpha will be Poisson by vector, it's inverse of this omega times derivative of T. So all in all, this is going to be minus Z dot B dB T alpha. Oh, index down. That's what it amounts to. Okay, and then there is a second term, which comes from here. And it is a variation of Lagrangian by lambda is just T, right? And delta lambda, let me remind you, is epsilon dot. So we have another term, which is epsilon alpha dot times equations T alpha. And it looks like I need an overall, and all this comes with minus. Now it's correct here, because in the Lagrangian, we have this term with minus, right? Minus lambda alpha T alpha. So if lambda transforms by epsilon dot, we just get minus epsilon dot T. That's what I'm reading here. So then we take a sum of these two. And this is, of course, nothing but epsilon alpha T alpha dot. So it's a total derivative. And under standard assumptions, it is a symmetry of the action, right? So we call symmetry something which preserves the Lagrangian up to total derivative and hence the action up to boundary term. That's how it is, and this is precisely this boundary term, right? Okay, so if we, for instance, assume that our gauge parameter epsilon vanish at endpoints, for instance, at minus infinity in time and at plus infinity in time, then it gives 0, right? So we checked it. And exercise, find delta lambda alpha explicitly in general case, where these assumptions are no longer correct. But still, we have a first-class constraint. So this is 0 only on the constraint surface. So means modular terms proportional to the constraints. For the moment, the simplified assumptions were that these guys vanish identically, explicitly in the general case. Case, let me even do it explicitly, which case is when T alpha H is equal to V alpha beta T beta and T alpha T beta equals to U alpha beta gamma T gamma. So this is a general case. Okay, good. So let's consider example. And the example, to see how it works, of course, there are many examples in field theory, including the Maxwell system, which is also a good example. It will be the second exercise, but let's start with something just mechanic, something from mechanics and still physically relevant. So let's consider the Hamiltonian system for relativistic particle. So it reads like this. It depends on x, p, and Lagrange multiplier lambda. These are now 4-dimensional. Because we are speaking about relativistic system, our integration parameter is not necessarily time coordinates, because in our reference frame x naught is a genuine time, but tau is just a certain parameter parameterizing a walled line of our particle. So it's an integral of over d tau of p mu x dot mu. Still, I use dot to denote derivative with respect to tau, minus half lambda p squared minus m squared. And so we have one first-class constraint, which is a mass shell condition. So p squared minus m squared equals 0. That's the equation, constraint equation. Constraint is just, you better put it like this, is t. That's the constraint, and here p squared, what I mean is, of course, it mu nu Minkowskian metric p mu p nu. Okay, good. So let's check, let's see what gauge, and it is constant for the moment. So we work in inertial reference frame, which means that our metric is just a standard Minkowskian metric. Okay, what are our gauge symmetries? Let me remind you that delta x mu is going to be x mu is t times epsilon. Epsilon is our parameter. So, and our constraint is p squared minus m squared with 1/2, because, let me put it like this. So what it gives us? It gives us xp, it gives us p mu epsilon tau, right? Delta p mu is 0 because it is constant, and p commute, Poisson bracket commute with momenta. And then finally we have delta lambda equals to, there is no Hamiltonian here, there is nothing, so it's like an example before, it's simplified setup, and delta lambda is just epsilon dot. So we see that this is a gauge system, right? Can you hear me? Is everything fine?
Yes, we can hear you.
Okay, good. Well, as anyway, I interrupted. Are there any questions for now?
For now, I think no.
So yeah, so we have a very simple example of a first-class system which we considered before. It is of direct physical relevance. It describes particles, relativistic, and in such a formulation, it is a gauge system. So what is the meaning of this gauge invariance? Any ideas? What it corresponds to? Somehow we don't see unphysical degrees of freedom here, right? Because we have just coordinates, momenta. So why do we suddenly get this gauge invariance?
Parameterization of tau, maybe?
Yeah, eventually, yeah. And this is an exercise. So exercise. Indeed, this system is a reparameterization invariant. So to understand this, so first of all, first part of the exercise is eliminate pi mu, assuming this is important assumptions, and it will be clear why it should be so. So lambda should not vanish. So if lambda is non-vanishing, then we can eliminate p mu. These are auxiliary fields, and this is going to give us the usual first order action, which looks like this. This is simple. This is just elimination to make sure that we get to what we know. And second is to relate these gauge transformations to geometrical gauge transformations. which means reparameterizations. What do I mean? I mean that this X, so we can think of X mu and P mu as scalar fields on a walled line, and lambda as a one form. So we have fields X mu of tau, P mu of tau, and lambda, we can think of it as lambda of tau d tau. It's a one form. And then the action is, of course, our action is just integral in the sense of integration of differential forms on one-dimensional manifold of P mu dx mu minus half lambda t, right? But now lambda is a one form, we integrate it over walled line, and P is zero form, X is zero form, and D is the Ram differential, which is a one form. So it's a one form. So from the way this action is written, it's clear, because we know that integration of differential forms is an invariant operation. You can do it in any coordinate system you like. So I can do, instead of tau, I can use different parameterization of my walled line and get exactly the same result. So this action clearly has a reparameterization invariance. But if I write down this, how these reparameterization invariance act on fields, I'm going to see the following. I know it should act on field by Lie derivative. Now my objects have clear geometrical meaning. X and P are scalars from the point of view of walled line. And lambda is a one form. So I know that delta epsilon, well, let me use different convention for a parameter. Delta psi of X mu is just of course, just psi x dot, right? Just a usual shift term, how scalar field transform under diffeomorphism. The same exactly for p mu. It's just psi p dot mu. And but lambda is a in this convention, lambda is a one form. So delta lambda, let me write it like this, is of course just Lie derivative with respect to the vector field psi d over d tau of such a one form d tau. So you can compute it. And it is not just, it is not psi dot. It has second term. If you compute Lie derivative, it's going to be something like psi lambda dot plus lambda psi dot, if I remember correctly, d tau. You see, so we have a different transformation law. So the question is how these transformations, which we see here, these transformations, the one of first-class constraint system, what they have to do with these transformations. It looks like the origin is the same, but one has to understand why it is actually the same story. And a good way to a simple, well, a somewhat simplified version is to eliminate P, to trace how gauge transformation act on the reduced action after elimination of P. It acts on lambda and on X, and then relate this with transformation of X and lambda in this geometrical way. In fact, there is just a certain redefinition of parameter which compares the two. So indeed, it is correct that this gauge transformation, which we see immediately and automatically from this first order formulation, is just a different basis for the standard reparameterization invariance of a particle model, which I'm sure you all heard about. But this also explains why, at least for these wall line models, one-dimensional relativistic particle models, this Hamiltonian formalism is very useful. Because if you work in terms of extended Hamiltonian action, you consider these systems as first-class constraint systems. You automatically know gauge transformations. You are sure you missed no gauge transformations. Then you know how to derive the most standard second order formalism just by elimination of momenta. You can also continue this and eliminate lambda. Together with some gauge fixing, you can get to the standard action for massive. If mass is non-zero, you can also get a standard action for a massive particle, like from Landau-Lifshitz book. So somehow it's like the most powerful formulation, if you want, because you can arrive to all other formulations just by elimination of auxiliaries, and at the same time you automatically know, because you know first-class constraints, you know your gauge symmetries. And this is a very attractive feature. So at least for particle models, this Hamiltonian formalism is probably the best way to handle them. And this is not the end of the story, because once it gets to quantization, to quantum theory, then it's even more convenient to work in terms of this first-class constraint system. Otherwise, you just don't know how to quantize. Or you meet some other difficulties which are kind of unnecessary in this setup. Unfortunately, things are not so simple when we go to field theory, because by using Hamiltonian formalism in field theory, we lose manifest covariance, because we need to explicitly split our space-time into space and time. And this is a very important drawback. Still, in some situations, it's almost unavoidable, the usage of Hamiltonian constraint formalism, but otherwise, it's of course not the best choice. But to understand, as the simplest example of gauge systems and what can happen if you have gauge freedom, I believe this constraint Hamiltonian systems provide the best possible pedagogical example, and not only pedagogical, because these systems make sense, and in fact their quantization is also very important for describing already relativistic fields. We will get to this. Okay, so so far so good, and I think so. The problem here is to relate gauge symmetry. Symmetry to reparameterizations. Okay, and another exercise is to find gauge symmetries of Maxwell, because we is a first-class system. Then eliminate eliminate momenta pi I and check that we indeed get the standards, the ones which we know from electrodynamics, the relativistically covariant form of gauge transformation of Maxwell theory. Okay, good. Then we can slowly move to indeed this more advanced approach to constraint systems and to gauge systems in general. But before, which is BFV approach, but before that, I need to say a few words about what I have not discussed. So I have not discussed more general systems where we have first class and second class constraints at the same time. This is a bit technically difficult, but conceptually there is nearly nothing, because what you actually do, you extract second class constraints and go to, from the mixed set of constraints, and go to their surface, which is again symplectic manifold, and you are back to first class setup. Or alternatively, you pick like half of second class constraints and treat them as first class. It's not a very usual not a very usual situation, and it so I decided not to spend time on this, because it's not so often that it is really necessary to handle like mixed setup where you have both first and second class constraints. Okay, and having said this, let us slowly move to BFV. BFV for formulation, well, better even quantization, call it. But to begin with, it will be just a formulation of classical system, and then we will use it to quantize constraint systems, and it will be clear why it is so convenient to do it in this approach. Okay, so the idea is a bit strange. So at first glance, of course, the idea is to embed our M, which I now going to call M naught, our phase space, to extend our phase space by extra variables to like M, which contains our M naught, and M is a extended phase space, which is a supermanifold. So, and I denote by A functions on this supermanifold. And standard example is that what I do, I take A to be functions on my phase space M naught, tensor product with polynomials in variables C alpha P beta, but they are anti-commuting. So I denote the Grassmann parity of F by F. So what I'm trying to say is that Grassmann parity of our phase space coordinates is 0. In the simplest case, in general, it can be system with fermions, so there can be, but now I want just a simplest example. So all my phase space coordinates are bosonic, so they have Grassmann parity 0, they commute. But Grassmann parity of these guys is 1, so they anti-commute. So in particular, these polynomials in anti-commuting variables is a finite dimensional algebra. It is, for those who know the name, it's just a Grassmann algebra generated by these variables c and pi. Do you know what Grassmann algebra is? Have you ever met fermionic variables? I wonder how many details should I give about this?
Maybe it would be good to see an overview, because I'm not really strong in that. But I don't know the rest of it.
Okay, we really don't need much. So what is important? If we have some, let's say this variable c alpha, for instance, if we take polynomials with, for instance, real coefficients on c alpha, and suppose we have an element from there, what it looks like? It looks like f is like f naught plus f alpha c alpha plus f alpha beta c alpha c beta, but because c alpha's anti-commute, so c alpha c beta equals to minus c beta c alpha, so they behave precisely like basis differential forms, and in fact somewhere deep inside you can think of them as differential forms, but let's don't get into this geometry. And we can continue like this, but in contrast to usual polynomials, this thing stops at alpha 1, alpha m, where m is a number of variables c, right? C alpha 1, c alpha m. Why? Because these coefficients, because c anti-commute, these coefficients can always be taken to be anti-symmetric tensors, right? Because c, just like when we write Taylor series of polynomial, we can assume indices to be symmetric with respect to these tensors, to be symmetric with respect to exchange of the indices. Now it is anti-symmetric because c anti-commute. The order does not matter, but you need to remember the sign change if you take one c through another c. That's why this expansion in C stops at order m, where m is a number of C variables. So it's a finite dimensional algebra, of course, the same with pi, and also C with pi, they also anti-commute, right? Because both of them have degree 1. Sorry, P beta C alpha. So they also anti-commute, same for P. So this a nice intuitive way is to think of this C and P as like additional coordinates on our phase space, which are like special, like fermionic coordinates of different type. But if you are not easy with thinking in geometrical terms, you can simply think in algebraic terms, saying that all I do is, instead of considering functions on my phase space, which we studied for a few lectures, now I consider functions on my phase space with values in this Grassmann algebra, in these polynomials in anti-commuting variables. This is the main thing which we need, but still it's useful to use some geometrical concept. For instance, you can easily define what is derivative with respect to such a variable, just saying that if you, well, for instance, what is the derivative with respect to C1, right? And here you have some, it's enough to do it for monomials, right? You have some C, and if somewhere inside you have C1, and you can't have it two times, because if you have C1 2 times, then it is 0. because it anti-commutes. So C1 squared is 0. So what you do, you use the anti-commutation relation to pull C1 in front and to cancel it. So in particular, d over dc1 of C1 is 0, and d over dc1 of whatever C1 in the, sorry, this is 1. This is 1. But d over dc1 of whatever not depending on C1 is 0. That's actually plus Leibniz. This defines derivatives. And this is very useful to still have an analog of differential calculus for such strange spaces. But in fact, these spaces are much simpler than the usual real ones because algebra of functions is finite dimensional. There is no topology. There is nothing. It's just a nice way to think about these algebras, to think of them as algebra of functions on certain superspaces. Okay, with the time we will have more examples, and I will have more. I will give more comments. Okay, but in addition to this, it is important that we have not only this Grassmann degree, but strictly speaking and in general, we have also additional degree, which is called Gauss degree, because these variables are called Gauss fields or Gauss variables. Gauss degree, and this degree is a Z degree, and it is assigned such. It is denoted by well, it's in different places. It's denoted differently, but I use this traditional convention. So we prescribe the degree of C alpha variables is 1, and degree of P alpha variables is -1. If M is a real manifold, so which means that we don't have fermionic phase space coordinates, then Grassmann parity of F is just Gauss degree of F modulo 2, where F is an element of our big algebra. Let me recall you that big algebra is this one, of functions on our phase space with values in our Grassmann algebra. But if, for instance, we have some of the coordinates on our phase space are fermionic, which is physically important. For instance, if you want to describe, I don't know, spinors, for instance, electrons, positrons, and other particles like this, you need fermionic fields. And they have Grassmann degree 1, but Gauss degree 0 because they are physical fields. They are not associated to gauge symmetry. So in general, there are 2 degrees. But in the simplified setup, where we don't have physical fermions, it is just like this. One is Gauss modulo 2, so we can strictly speaking forget about Grassmann degree. But in general, we do need Grassmann degree if you want to describe system with physical fermions, or for instance, supersymmetric systems and things like that. But to understand the idea, it's enough to restrict to this simplest setup. Okay, so we have this algebra, and then we make it into Poisson algebra. And so A is an algebra of functions on extended phase space. So it's a phase space extended by these Gauss variables. And there is a Poisson bracket on this extended space for which C and pi are canonically conjugate. Poisson bracket. So what we have that so our ZA, ZB was like before, sum omega A B O Z. But in addition, we have C alpha P beta. We take it to be delta alpha beta, and they commute from different sectors. They commute. So ZA with C alpha is ZA with P beta and is 0. So this defines the Poisson bracket. But what is important, now it's a graded Poisson bracket. So what we need to require, properties of these properties. Actually, now it's part of definition, because what I wrote does not define Poisson bracket. It only defines Poisson bracket for coordinate functions, but we need for generic functions. But using these properties, we can get it. We can get a general one. So properties. So of course it is graded. It's called graded antisymmetric. So before we had a super Grassmann variables, it was just minus bracket G with F. But now we get a sign factor. It's 1 plus. Or we better write it like this. It's still the same minus. But here we have minus 1 to power multiplication of degrees GF. Then we have graded Leibniz rule, which is F GH equals to F GH plus, again, minus 1. So what happens? You should think of like operator of taking a bracket with F going through G. So the rule, just like when you commute these variables, the rule is if something goes through something, which commute in normal situation, here you get a sign, additional sign factor, which is proportional to the multiplication of parities. So in this case, it is parity of F times parity of G, and here you get G F H. You see why you get this? Because this F went through G. And this sometimes is called Koszul sign convention. So if something moves through something else, you get an additional sign factor of this type. And finally, Jacobi, which is also graded Jacobi. Let's try to write it correctly using this idea of this sign rule. GH is what it should be. Again, what is Jacobi identity? It's like an operator which takes a bracket, a Hamiltonian vector field. Okay, it's a first order differential operator which takes a bracket with F. It satisfies Leibniz rule for the Poisson bracket. So it first hits G and then it hits H. That's the simplest way to remember Jacobi identity. But now we should get a sign factor. So what we get? We get FG. Nothing moves through anything. Just bracket moves through bracket, but bracket has degree 0. It's clear from the definition. Plus, and here we get now the bracket with F should go through G. So again, we get a sign factor of F times G. And we get G F H. So this is the Jacobi identity. Now, if we know the Poisson brackets of coordinate functions, we can extend our Poisson bracket to generic functions, right? And it can be written, actually, nice way to write it is like this. I'll write it in a slightly more general form. It's in the form which is going to be also correct for the case when among Z there can be Grassmann variables. Oh, wrong arrow. So what arrow means? If you take a derivative with respect to odd coordinate, you need to decide where you differentiate. So, for instance, left and right derivatives. Right derivatives. So, for instance, d over dc of Cp is P, but same thing acting from here, d over dc is going to be minus P, because this comes from the right and should go through P. So the rule of the right derivative is of course very simple. It's the same. You just need to take this variable with respect to which you differentiate. You need to take it to the rightmost position, and then just to cancel it. This defines. But this changes the sign. And in general, if we have a d over d, I don't know, psi alpha of f, it equals 2 minus 1 to power f plus 1 psi alpha f d over d psi alpha. It's easy to check exercise. It's a simple exercise, not a real one. It's useful to have this convention. Of course, in principle, we can get away without introducing. Can you hear me? Is everything fine? Because my headset's fell down. Yeah, I see.
Yes, it's
okay, good. So yeah, this notion is not necessary, but it is very useful because it's nice to write some formulas using left and right derivatives. They become more intuitive and easier. Okay, so what is important? Note, for instance, that if parity of A of function f, for instance, function f is 1, then Poisson bracket f with f is not necessarily 0. It can be 0, of course, but it's not necessarily. Why? Because, look, the symmetry properties of our Poisson bracket are like this. So if we exchange the argument, we get minus and extra sign. But if both entries are fermionic, which means have degree 1, Grassmann degree 1, if we exchange, if we compute this is also minus. So we get to minus, so it's plus. So it's not 0 on symmetry grounds. Like in usual mechanics, Poisson bracket of a function with itself is always 0. Here, it's not the case, and in fact, this is quite a non-trivial and interesting equation, which we are going to use soon. Okay, so in fact, yeah, maybe I should, if you asked to give some more background about this graded story. So A, in general, is a Z-graded associative and graded commutative algebra. So what does it mean? It means that A is a direct sum as a linear space. It's a direct sum components of degree I. They are called homogeneous components. They are formed by functions which have Gauss degree I. And then multiplication is Aij belongs to Ai plus j, right? Because product of two functions of definite degree has a sum, as a degree, it has a sum of the initial degrees, right? And also that fg is -1 to power fg gf, which means graded commutative. Now I forgot about super. So suppose that we don't have fermions, so there is only one z degree, and this is this Grassmann degree is just Gauss degree modulo 2. So this type of algebras often appear in applications, in modern applications, relatively modern. It's of course all known for quite some time, and yeah, here of course it's a case where this is just Gauss modulo 2. Otherwise, we need to speak about Z-graded associative commutative superalgebra. So there are like two compatible structures, but let's forget about fermions for the moment. It's always easy to add. Let's just get used to this graded setup. So we assume that our systems do not have physical fermions. So all phase space coordinates commute, then we don't need to bother about this second degree. If we need, you know that it can always be done. Okay, and what we saw that also our A is a Poisson algebra. The particular one we constructed out of phase space is a Poisson algebra. So it is graded Poisson algebra, strictly speaking. Let's say graded Poisson algebra. So this is our main setup. Okay, and what is now we can actually define the simplest instance of this BFV formulation. So definition. So BFV system is this graded Poisson algebra A, where we specify an element omega from A, which has degree 1. Well, let's be general and also ask it to be Grassmann, to have Grassmann degree 1. If we don't have physical fermions, then this second requirement is not necessary. Then we have, and this is called BRST charge. So BRST is abbreviation of few names: Becky, Ruiz, Stara, and Tutin. Charge. And Hamiltonian. Then we have extended Hamiltonian. Extended Hamiltonian. H such that Gauss of H equal to parity of H equal to 0. And the conditions are satisfying. So the main one is this. Do you remember this is a non-trivial equation because omega is fermionic, it's of degree 1, and omega h is 0. So this condition is sometimes called master equation in this context. of course, the Hamiltonian version, but it's also deeply related to what is known in math under the name of Maurer-Cartan equation. And this is, of course, just a definition, just a condition that H is invariant with respect to symmetry generated by omega. Somehow it is something that controls the gauge invariance of the Hamiltonian. So that's the definition. Of course, this definition is to be supplemented with physical interpretation, because otherwise it's just a mathematical object. And maybe, of course, we will repeat and study more carefully next time, as our time is over. And so the exercise here would be to check that in the simplified setup where T alpha H naught, now old objects which are not BFV, I put not, so it's an initial Hamiltonian. T alpha H naught is 0. T alpha T beta is 0. Then you can take omega to be C alpha T alpha and H to be H naught. And this gives BFV system. And this is the simplest possible BFV system, which is constructed by embedding a simplest first constraint system where you have zeros here into this BFV setup. So it's very simple. In general, of course, there are further terms, and we are going to study what they are and what all this is needed for. So thank you very much. And let me remind you that I'm not sure I can, because I'll be on travel, so it's difficult to promise. I'm not sure I will be able to give a lecture on Friday next week, but I'll write you before. Maybe we will move this to the week when I will be in Moscow. But on your side, you tell me which time slots in the, let's say, second half of the week, starting from Wednesday, are available for you for an additional lecture on the week of April 15th and the one after that. Because I would prefer to have few lectures offline rather than online. I hope you agree with me. So let me know what are options. Thank you very much. Questions?
I'm sorry, but what does BFV stand for? How is it justified? Maybe I didn't.
Oh, yeah. This I forgot. This is, yeah. Let me do it somewhere. It's Batalin, Fratkin, and Vilkovisky. So it's a Hamiltonian version. So the title of our course is Batalin-Vilkovisky, just this. But these are very closely related things. It's difficult to distinguish them. So this is like Hamiltonian version, if you want. And this is Lagrangian version of the same thing. But historically they are called like this, but they are so deeply related that it's probably doesn't make much sense to distinguish. But the idea is that this is Lagrangian version and this is Hamiltonian. And as we started with Hamiltonian constraint systems, we first meet this BFV version. It's purely terminological and historical.